If you've never built a radio transmitter before, watch this video. In it, I'll show you how you can build a transmitter for under $20, yet can be heard hundreds of kilometers away. It's super simple and takes less than 2 hours to build. You could even get it on the air tonight. There's no soldering and all parts are easily obtainable. It could hardly be simpler. It uses just one transistor and fewer than 20 other parts, and just needs a screwdriver to put it together. It's an ideal beginner or club training project. There's no better way to show the magic of radio than to build a transmitter like this. All parts are readily available, and the construction time means that if you've got all the parts, you can have it going in only a couple of hours. And it can be heard over hundreds of kilometers distant. You can build the transmitter on a piece of kitchen chopping board. The components are screwed to it, meaning there's no soldering. Because I've used this board for multiple different projects, there are holes at 1 centimeter squares. See my earlier video where I described the chopping board construction in more detail. Something I really suggest is doing the same as I did and having the holes at 1 centimeter spacing. That is, if you're going for this construction approach. I also suggest numbering them with the letters going up from left to right and the numbers from bottom to top. That way you can use a letter number coordinate and share details of projects with other people that might also wish to build the same project on their own board. Now to the description of the transmitter. It is a 1 transistor crystal oscillator. The circuit is called a Pierce configuration, though you don't really need to know that. The crystal, which sets the frequency of the oscillator, is just below 3.58 megahertz. Might actually be marked 3.579 or something like that. Anyway, that frequency is a commonly available crystal, available very cheaply, and it also happens to be in the 80 meter amateur band. So if you've got a crystal, you just add 1 transistor and a few components, and you have an oscillator, which is basically a little transmitter. The output from just a 1 transistor oscillator is quite dirty and full of harmonics, so there is a filter following that. That filter chops off the other frequencies that are generated. These are called harmonics and are basically multiples of your basic fundamental frequency. In this case there will be harmonics near 7, 10.5, 14 megahertz and so forth. The filter comprises some disc ceramic capacitors and some RF chokes, which are actually inductors. If you want to read up more on that, it's called a low pass filter, with a cutoff frequency around 4 megahertz. That means it passes everything under 4 megahertz and rejects frequencies above it. The more filter sections you add, the more the roll-off, meaning there's even better harmonic rejection. A transmitter is a radio frequency generator. There's different ways of controlling its frequency, but the simplest and cheapest is to use a quartz crystal. This particular one, 3.5795 megahertz, is very cheaply and commonly available. Another good thing about it is it happens to be in an amateur band. Therefore, you can use it to control a 1 transistor circuit to build a small transmitter, which is what we're doing today. Compared to other ways of controlling the frequency, crystals are very stable. That means they don't drift very much in frequency and give you a fairly clean output. Their main disadvantage is that they are locked to a single frequency, with only a very small variation around it possible. So you basically have to accept the frequency on the crystal can. Anyway, that doesn't matter so much for this exercise, as this is an ultra simple transmitter, and the simplest transmitter you can build that's reasonably stable will use a crystal. Just to the right of the crystal is a resistor, the only resistor used in this transmitter. It has a value of 22,000 ohms, or 22k ohms for short, k meaning 1,000. The function of this resistor is to provide some current to the transistor's base connection. Without that, the transistor will not operate. Speaking of the transistor, here it is in the center of the screen. It is the heart of the transmitter. It is what provides the gain necessary for the circuit to operate as an oscillator, with the addition of feedback. Another thing about the transistor, unlike all the other parts, is it has 3 wires coming out of it. They need to be connected correctly, otherwise the transmitter will not work. The 3 leads on a transistor are collector, base and emitter. Because this is an NPN transistor, the collector goes to the positive connection via some other parts that I'll point out in a moment. The emitter goes to the negative connection, otherwise called earth, and the base goes to a connection in between, with current provided, as I mentioned before, by the 22k resistor. The crystal is connected between the base and collector with a capacitor in series. That's the thing that looks like a lentil just above the center of the screen. This is where the power goes in, but it's via this part here called an RF choke. It looks a bit like a fat resistor, but it isn't. It's actually a coil of wire that's wound very tightly. The property of the RF choke is it passes DC current from the positive 12 volt power supply that goes into the transistor to power it up, but it stops radio frequency signals from passing through. That's important because another role of the collector in this transistor is the output connection. This is where the radio frequency signal that's generated by this oscillator comes out of the collector and is passed onto the subsequent filter stage. So we actually want the RF output to go this way. We don't want it to go any other way. So we've got this RF choke here to provide some isolation to stop it from doing so. Another connection on the transistor is the emitter. As I mentioned before, that goes straight to earth, or negative, or ground, when the transmitter is transmitting. But as we're wanting to send Morse code signals, there are times when the transmitter is not operating. The easiest way to shut the transmitter off is to lift the emitter lead so that it's no longer making contact with the earth or the negative terminal. When the emitter lead is lifted, there's no longer a circuit for the current, which in conventional current parlance goes around from positive through all this oscillator circuit back out to negative, and when that's interrupted, of course, the thing is not operating. You can see a wire going from the emitter to the ground, but we'll have a closer up as it's not actually permanently connected. It's a crude Morse code key, which is really nothing more than a switch. If you want the transmitter on, you press it, which completes the circuit, making contact between the emitter and the earth or negative. And if you don't want it to be on, then you just leave it like this. No current can pass through and the transmitter is disabled. I should mention that this transmitter is built just like you draw a circuit diagram. That is, you have the negative, the ground or the earth along the bottom, and at the top you have the positive rail where the plus terminal of the battery connects. The component here is the coupling capacitor that passes the radio frequency signal through from the collector of the transistor to this low pass filter. That has 2 inductors, both of them are 2.2 microhenry, and some capacitors. All of them are 820 picofarad. I've actually used two lots of capacitors here. They're in parallel, and when you have two 820 picofarad in parallel, you double the value, so it becomes 1640 picofarads or 1.6 nanofarads. You don't actually have to do that, but because it's sometimes cheaper to buy capacitors in bulk with a larger quantity and it simplifies ordering, that's what I've done here. There's a couple of other parts I haven't talked about yet. This is a capacitor that goes straight from the positive connection to the negative connection. That just provides, if there's any RF floating around, then it just shorts it to earth, because you don't want RF in certain parts of the circuit. And right here across the emitter, between the emitter and earth, is another capacitor. Similar value, it's 10 nanofarad or 0.1 microfarad. The value doesn't really matter. You could even make it 10 times bigger and have it nanofarad, or I should say 100 nanofarad or 0.1 microfarad, and it would still be okay. The capacitor here just makes the keying a bit smoother. And similar comments as to the value with this capacitor is here. It's 10 nanofarad, but it could just as easily be 100 nanofarad or 0.1 of a microfarad. Whereas some of the other component values, especially in the low pass filter, they are a bit more critical and you should follow them. Right here is a power socket that just goes to the 12 volt power supply. You could try using this transmitter off a lower voltage, but the output power will be less and the signal put out will be weaker. What about a 9 volt battery? Well, you could try that, but I don't suggest you do, because 9 volt batteries aren't designed to give very much current, and this transmitter probably draws a bit too much for you to be using it for a long time with a little 9 volt battery. Plus they're quite expensive. Right here at the tail end of the low pass filter is the antenna connection. I've got that going to this socket. It's a well-known type of socket called a BNC, but you don't necessarily have to use that. You could just connect 20 meters of wire to this screw, and that can operate as an antenna. It's a quarter wavelength on 3.5 megahertz, and we know that because the wavelength of 3.5 megahertz is 80 meters. It's approximately 80 meters, near enough. And a quarter wavelength antenna is resonant and will work with a transmitter like this. It is also desirable to have a ground connection. That could be another piece of wire 20 meters long, or if you've got a cold water tap or stake in the ground or anything like that, then you could connect something to that. This is the circuit diagram. If you haven't already, I suggest learning some of the symbols. There's only a few unique symbols in this diagram, so I'll point them out now. The zigzag line is a resistor. There's actually different types of diagrams for resistors. In some countries, particularly Europe, they just show it as a rectangle. But anyway, that's the resistor here that resists the force of current. The two plates you see here, there's quite a lot of them in this transmitter. They are all capacitors, and there are different values. Some of them are picofarads. They are smaller values of capacitors, like here and here. And the larger value of capacitors are nanofarad. A nanofarad is 1000 picofarad. And then there are other capacitors. This one, 10 nanofarad, is even higher. 10 nanofarads are here. And an alternative way of expressing them is microfarads. So 1000 picofarad is 1 nanofarad. and 1000 nanofarad is 1 microfarad. So 10 nanofarad is also the same as 0.01 of a microfarad. The other important symbol you need to be aware of is right here, which is the quartz crystal, 3.579 megahertz. Now, the only important thing is that it has to be in the 80 meter amateur band. Unless you want to do this just as an experiment, if you are not going to connect this to an antenna, then you could use a crystal on a different frequency. But in this case, we want to connect it to antenna. We want to see how far it gets out, so the crystal needs to be in an amateur band. 3.579 megahertz is a common frequency. Another frequency that is less common is, I think it's 3.684. You could use that instead. Just substitute it in. There's no need to make any other changes to the circuit. The coil of wire you see here is an RF choke, and they are used in two parts of the circuit. In this case, between the collector and the positive rail here, and also here. 2.2 microhenry. These ones are for the low pass filter, which cuts off around 4 megahertz. The coil here is a bit bigger in value at 22 microhenry. And this right here is the transistor, the BD139. There's 3 connections. It's an NPN transistor. Collector goes to the top of the circuit or towards the positive, emitter bottom of the circuit towards the negative. And the connections of this are super important. I'll just give you a close-up of the pin-out connections here, and this is with the writing of the transistor facing you. That's very important. Writing has got to be facing you, and for the BD139 transistor, then these are the connections and where they go to. And how it's actually in the circuit, that's the emitter. That's the collector in the middle, and the one on the far right is the base. If you've got an external Morse code key, you can connect this in instead of this floating piece of wire. You'll note there are things in yellow circles. These are the grid coordinates on the chopping board. For instance, the base there is shown as B3. If you look at where the base is connected to, which is here, then that is B3. There's also D2, that's the emitter, and going up a number, D3, which is the collector. The RF choke is going up to D7, and D7 has quite a lot of other connections. It's got the top of the 22K resistor, and 10 nanofarad capacitor here, and the supply rail, and you can see that all right here. Going across the bottom, everything that is earthed goes to 1. You will need some extra wire to complete all these connections because the component leads by themselves won't be enough. I suggest building from left to right, following all these coordinates. This is the parts list. It's very short. Just one transistor, a BD139 NPN transistor. You could use other types of transistors. I haven't tried them in this circuit, but the circuit should still oscillate, but I don't think you'll get as much RF output power as with the BD139. So I strongly suggest BD139. 22K resistor. I've said it's a 1/4 watt as that's the most common type of resistor you can get. Doesn't matter if it's 1%, 5%, it's not that critical. It should only cost you a few cents. You might have to get a few in a pack. That doesn't matter because it's a common resistor value that you'll be using in other projects. The lowest capacitor value we have is the 220 picofarad. That's a disc ceramic capacitor that, as I mentioned before, looks like a lentil. Just need one of those. 820 picofarad, that's the next highest value. We need 4 of them, also disc ceramic, and that is used in the output low pass filter. There's a 1 nanofarad here. That's the coupling capacitor between the oscillator and the low pass filter. And 2 10 nanofarads, also disc ceramic. Doesn't matter if it's not disc ceramic, and the value is not critical either. It could be 22 nanofarad, could be 47 nanofarad, even 100 nanofarad. Won't make any difference, but you need 2 of them, and again, a very common component value. 2.2 microhenry RF choke. Need 2 of them for the low pass filter. There's another one, a bigger in value, 22 microhenry, need that as well. The crystal, 3.5795 megahertz or 3.58. Doesn't have to be really exact, but it should be in the 80 meter amateur band. So if you can find a crystal for even 3.68 megahertz, that would be okay. Just a different frequency. A 12 volt power source just needs to give you a few hundred milliamps. You could use something like a battery or several batteries connected up. Just needs to give you, say, between 12 and 15 volts. That would be fine. Screws and washers, just need them to hold all the parts together. And of course the chopping board, I spoke about that in the earlier video. Insulated wire for antennas. Yep, you need an antenna. If you're going to be heard anywhere, an antenna is important. When you are ordering parts, make sure you order something little extra. It's a 47 ohm resistor. The reason for that is that will be helpful when we're testing the transmitter. It is what we will call a dummy load. This is the battery that I'm using. It gives you 12 volts. It's quite a hefty and strong battery. You don't have to have something this big for this type of transmitter. I said before the 9 volt battery was a little bit too small, but if you just wanted something that was using dry cells, then a pack of 8 alkalines, and you can buy battery holders quite cheaply. 8 AA's will give you 12 volts, so that would be absolutely perfect. Alternatively, you could use rechargeables like 18650s. They give, I think, about 3.7 volts each, so 3 of them will give you just over 11 volts, 4 of them will give you about 16 volts. So either of those battery combinations will be fine for this little project. What I'll now do is do some voltage measurements. To the right is a multimeter. I've just got it set to 40 volt maximum setting, so just choose a setting that is higher than your 12 volt battery, so anything above 20 volts would be fine. And the purpose of this is just to do some probing around to make sure that the voltages are what they should be. I'm not pressing the key yet, so the transmitter is not operating, but when I touch D7, it's D7, which is the power supply. That's where the red probe is, and anything along the bottom, anything along the 1 row, should be all the same. If it's not, then you've got problems. Anyway, we're just getting just over 13 volts, which is fine. I'll keep the black lead, or the negative, on the 1 row, and we'll probe around and see what else, where there's voltage. On the collector, it's again just over 13, which is what you'd expect because the RF choke here will be a short circuit, more or less, for DC. Now we'll try the base of the transistor, and it's still 13.38. Now, that's actually the same as the collector voltage, which looks unusual, but it's because right now the base or the transistor isn't drawing any current. We haven't got this thing switched on, so no reason for this to be much lower than the supply rail. So that's okay for now, but you should really watch the base voltage when we turn this thing on, and we will just by pressing the key here on the emitter, and then the base drops a lot down to around 0.5 of a volt. Now we'll just check the emitter. That's 13 volts exactly. We'll just go back to the collector again. 13.4 volts. So it's usual for transistors to have a voltage drop between the collector and emitter. So this is with the transistor off, 13 volt. Now when we press the key, which turns the transistor on, that shorts the emitter to earth, therefore it should drop down to 0. Well, more or less, which it does. Now other parts of the circuit here are not easily measurable on a DC voltage range. That's because this capacitor here isolates DC. It only passes radio frequency signals, and RF signals are AC, and not only that AC, but they're also at a much higher frequency than we're used to. So even though we're pressing the key and we're transmitting, we're not actually getting any indication, which is how it should be. So you'll need some other way to determine whether this thing is oscillating or not. If you've got a receiver, then put the receiver around 3.58 megahertz, tune a bit either side, and you'll hear a strong signal if this is oscillating. Another possibility is, and you can just see this 47 ohm resistor I've got. Here I'm just putting the 47 ohm resistor temporarily across the antenna contacts from antenna here, which is N3. The other side of the 47 ohm resistor goes to earth. Just holding it like that, but it's important to have part of the finger in contact with the body of the resistor. Now with the other finger here, just pressing the key so the emitter is shorted to earth, and the resistor is gradually getting warmer. It's taking a while, but if you have it too long it gets too hot to touch, so that indicates that the output coming out of this is significantly more than 1/4 of a watt, which is what this resistor is rated at. I've brought the transmitter inside and I've connected it to this RF power meter. Maximum scale is 2 watts, halfway is about 0.5 of a watt. If you don't have an RF power meter, then a circuit that I described in a previous video, and I'll link below, is a way of detecting radio frequency. It's something I've called the Squeakie, and just runs off a 9-volt battery, so I'll just set it to just at the point where it stops oscillating. I've got the Squeakie's telescopic antenna right near the antenna connection for the transmitter, and when I press the key, the Squeakie makes a noise. This indicates that there's RF floating around and the oscillator is working. This is about the best antenna you can build for 80 meters if you want to test this transmitter with good signals. It's called a half-wave dipole. It's a horizontal wire 40 meters end to end long, cut in the middle with 50 ohm coaxial cable connected to the center. That goes straight down to the transmitter. It should be outside and as high as possible. 5 to 10 meters at the apex is okay. It's also okay if the center is a bit higher than the ends, so you can have the ends drooping down. But you don't want the angle between them at the center to be acute. This is a very basic antenna. It does take up quite a lot of room, but if you can fit it in, it will give you good results on 3.5 MHz. If you don't have the room, then a compromise antenna may be the only option for you, but you may still get some amazing results from this transmitter. Now an on-air test. It's about 7:30 PM local time, which should be a good time for 80 meter signals to propagate. You could ask another nearby amateur, if you know one, to tune around to see if they can hear your signal. Although it is likely to be very weak, given your transmitter is only half a watt. Another possibility, and this will give you a good idea as to the distance that you're being received, is to use an online Kiwi SDR. With a Kiwi SDR, you can put in the frequency and be able to listen via a selection of remote receivers all around the world. Visit kiwisdr.com and have a search for various online receivers in your country, or if your country isn't very big, in your continent. Basically, you're looking for ones within about 1,000 kilometers. This one here is VK3YE in country South Australia. It needs to be on the right frequency. If you're using a 3.579 MHz crystal, put it onto 3.580 lower sideband. That's important. If the frequency isn't right, you won't have any chance of hearing your signal. If you don't hear anything, try all the other SDRs within range. They vary a lot in their receiving capabilities, and ones, especially in the city, have a lot of noise, so you might not be able to hear your signal from them. Well, that was VK3YE. Let's try another. That was also a success. Not a strong signal, but readable. We'll try another one in South Australia. VK5PH, Ironstone Range. And a similar strength to the VK3YE one. Not strong, but just readable. This has been a more detailed look at the chopping board CW transmitter. Still one transistor, but this time on 3.5 MHz. to suit a more easily obtainable crystal. Although, if you can get crystals for 7 MHz, 7.159 is a common frequency, you could use that instead, just by changing the values in the pi network. The characteristics on 7 MHz are a little bit different, and you'll get greater range from it. Even if you aren't an amateur, there's no reason why you can't build this transmitter and take it to either another amateur to connect to their antenna or a radio club that will also hopefully have their own antenna. The benefit of that is that you can use their call sign to send the Morse, and you also are connecting to an antenna that is of assured performance. That will give you a bit better confidence that the thing will work and be heard over longer distances. As I mentioned before, the 20-meter wire thing might work, but really, for the low power of this, you're better off with a full-sized half-wavelength dipole, or at least a G5RV, which is what I was using from here. If you want to make contacts with this sort of transmitter, then there's a couple of things you might need to think about. You could put a more useful frequency there, one that is for the CW end of the band, down nearer 3.5 MHz. You will of course need some sort of receiver, unless you are to use an online SDR for the receiving, which is a possibility, and you'd probably want a bit more power than half a watt. You can certainly make contacts with this sort of power level, but the chances of getting them is higher with more power. So, hope you've enjoyed this video. It's your first transmitter, you can build it, don't need to be able to solder, all the parts are obtainable, and the cost is less than $20. And you can be heard hundreds, if not thousands, of kilometers away. For more information, I'd suggest having a look at my previous video where I talk about building the chopping board in a bit more detail. I'll have a link to that below. And for more on low power amateur radio, there are books that I've written like Minimum QRP, and also some antenna books as well, which could be helpful. There's also more information on QRP, or low power amateur radio, on my website at VK3YE.com. So thanks for watching, and if you do build this transmitter, and it's definitely ideal as a club or training project, then let me know how you went in the comments below.